Welcome back to the deep dive. We're thrilled you could join us today because we have a massive and, quite frankly, totally unexpected topic to cover.
Yeah, it really caught everyone off guard.
Completely. If you've been anywhere near a terminal or a tech feed lately, you already know the date. It is March 5th, 2026, and OpenAI just dropped an absolute bombshell on the developer ecosystem.
The surprise release of GPT-5.4.
Exactly. And to be clear, right up front, looking through the documentation we've gathered, this is not just an incremental point release.
No, not at all.
We aren't just talking about a slightly better chat interface or, a few extra languages supported. This looks like a fundamental architectural shift in how these models operate at their core.
How they're priced, how automated systems actually interact with them. It really is a watershed moment.
Right.
The entire engineering community is scrambling to update their mental models of what is possible. And the goal of our deep dive today is to unpack this release completely for you.
Because what OpenAI puts on their slick marketing landing page is, well, it's almost never the full story.
Never.
So here is our mission and our source stack for today. First, we are tearing into the official API documentation directly from OpenRouter.
Which gives us the raw specifications, the new parameters, and the updated pricing economics.
Second, we've got high-level technical reporting from Crypto Briefing to give us the broader industry context. But most importantly,
This is where the real gold is.
yeah, we are diving incredibly deep into the raw, unfiltered, and honestly sometimes highly frustrated developer reactions from the r/Codex Reddit community.
We want to see how this model actually behaves in the wild when you push it to the breaking point, which is exactly where systems engineering gets interesting.
Because the headlines right now are completely dominated by a few very flashy features. Everyone is talking about the new staggering context window of over 1 million tokens.
People are reacting to the historic unification of the general-purpose GPT line and the specialized Codex coding line into a single multimodal powerhouse.
And perhaps most radically, we are seeing the introduction of what they're calling native computer use.
Right, the ability for the model to bypass APIs entirely and directly interact with operating systems.
Moving a mouse and typing on a keyboard, just like a human operator.
Yeah.
Okay, but here is where I want to set the tone for this deep dive. I was reading through the r/Codex threads, and the tension is just palpable.
Oh, absolutely.
Because while the hype train is moving at maximum velocity regarding that 1 million token context window, the actual developers, the ones building autonomous agents and enterprise applications.
They are saying the real engineering breakthroughs lie elsewhere.
Yes, they are pointing to massive advancements in tool search efficiency. And more importantly, they are warning that pushing that massive 1 million token context window to its limit comes with severe technical and financial trade-offs.
It's a classic case of capability versus reliability, and that's exactly what we need to explore. We need to look past the spec sheet.
Exactly. So we are bypassing the marketing fluff entirely today. We want to focus on the system constraints. We want to meticulously map out the failure modes for you.
And figure out the practical implementation details for developers and automated evaluators.
Let's start by unpacking the architecture and the spec breakdown, because the unification of the stack is the first thing that jumped out at me.
It's huge.
For years, as long as I can remember working with these APIs, there has been a hard dividing line in the AI ecosystem. On one side, you had your general-purpose reasoning models, the standard GPT line.
They were your conversationalists.
Great for drafting emails, synthesizing massive documents, brainstorming marketing copy.
But if you asked them to write a complex, multi-threaded back-end service in Rust, they would often hallucinate libraries or write highly inefficient loops.
Right. And so on the other side of the wall, you had your specialized coding models, specifically the Codex line.
Heavily fine-tuned on GitHub repositories, Stack Overflow, technical documentation.
They understood syntax, logic, and software engineering principles deeply. But if you tried to get them to explain their code to a non-technical project manager, the output was incredibly rigid and robotic.
Fair mechanical.
But with GPT-5.4, that wall is officially gone. The documentation states they've finally merged the general-purpose GPT line with the Codex line into a single model. But why did this take so long? And why is it such a big deal for systems architecture?
To understand the magnitude of this, you have to look at the routing dilemma that systems architects have been fighting for the past 3 years.
Okay, the routing dilemma.
Historically, if you were building an advanced AI application, say an automated software engineer agent, you couldn't just use one model. You had to build a complex orchestrator.
Often utilizing a mixture of experts' approach on the application layer, right?
Exactly. You would use a generalist model, like a standard GPT-4 or 5 for the planning phase. The user submits a request, the generalist breaks it down into a product requirements document, and then your orchestrator steps in.
Let me guess. The orchestrator then has to copy all that context, package it up, and send it over to the coding specialist model to actually write the code.
Precisely. You had to route your requests to different models depending on the specific subtask, and every time you switched models, you risked context degradation.
Because the specialist might not fully grasp the nuanced high-level intent that the generalist understood.
Right, because the specialist is only looking at the technical prompt it was handed. GPT 5.4 essentially eliminates that routing dilemma entirely.
It creates a single frontier model capable of both high-context, nuanced human reasoning and rigorous production-quality software engineering output.
You no longer have to compromise, and you no longer have to build brittle routing middleware.
You have a unified system that can architect a complex Python script, execute it, debug it, and in the very same continuous context window, eloquently explain the architectural philosophy behind that script to a non-technical stakeholder.
That is going to simplify so many code bases.
But speaking of that continuous context window, we need to look at the numbers.
Yeah.
Because I pulled up the OpenRouter API specs, and the numbers they're officially listing are just wild.
They really are.
We are looking at a total context window of 1,050,000 tokens. And to break that down precisely, OpenRouter lists it as 922,000 input tokens.
So what you can feed it.
Yeah, and 128,000 output tokens, which is how much it can generate in a single response. For you listening and trying to visualize that, 900,000 tokens is roughly the equivalent of handing the model the entire text of the Harry Potter series, plus the Lord of the Rings trilogy, in a single prompt.
It is an absolute mountain of data. But of course, in cloud computing, nothing is free. The processing power required to calculate the attention mechanism across 1 million tokens is staggering.
Which brings us to the pricing structure. This is where I started doing some math, and I want to see if I'm looking at this right. OpenRouter lists the cost at $2.50 per million input tokens.
Okay.
And $15 per million output tokens. There's also a highly specific separate charge of $10 per thousand web searches, which we'll touch on later when we get to tool use. Now, $15 per million output tokens sounds kind of steep in a vacuum. But is it actually expensive when we look at the broader market?
It is crucial to contextualize those numbers against the competitive landscape and historical pricing of equivalent capabilities.
Yeah.
You can't just look at the raw token price. You have to look at the cost-to-quality ratio.
Sure.
In the sources we reviewed, specifically the intense debates happening on Reddit, users are actively comparing this to the economics of Anthropic's Opus 4.6 API.
Right. Opus 4.6 has been the darling of the heavy-duty reasoning crowd for a while now.
Exactly. And users are reporting a fascinating financial reality. They are calculating that running Opus 4.6 costs roughly $5 to achieve a specific quality metric of about 0.61 on standard developer benchmarks.
Yeah.
Whereas with these new Codex-derived models inside GPT 5.4, developers are hitting a significantly higher quality metric of 0.70 for less than $1.
But let me make sure I understand this. So for the same task, Opus 4.6 is costing $5 to get a passing grade of a D-.
Yeah.
But GPT 5.4 is costing less than $1 to get a solid C- or C.
That is the practical translation, yes. And while a 0.70 might not sound like perfection, in the world of automated code generation, that delta between 0.61 and 0.70 is the difference between an agent that constantly gets stuck in syntax errors and an agent that can successfully compile a working prototype.
That makes total sense.
When you extrapolate that financial efficiency across the massive scale of an automated evaluation system or an autonomous agent loop that is making thousands of API calls an hour to brute force a solution,
The economics have fundamentally shifted.
the return on investment for your token spend is currently unmatched here.
Assuming, of course, that you manage that massive context window responsibly,
Yeah.
which, judging by the forums, nobody is doing right now.
Definitely not.
But before we get to the failures, I want to dig into a new parameter I saw in the API docs that completely blew my mind. It's called the reasoning details array.
Oh, this is huge.
From what I'm reading, GPT 5.4 actually exposes its step-by-step internal thinking process before it delivers the final answer to the user.
This is perhaps the most significant architectural change for developers building agentic workflows. In previous generations, models operated like black boxes.
Right.
You fed in a prompt, the model spent a few seconds computing, and it spat out an answer. If the answer was wrong, you had no idea why it got it wrong.
Did it misread the prompt? Did it fail at a math calculation halfway through?
Did it retrieve the wrong piece of data from memory? You had to guess.
We actually have the usage stats from OpenRouter to show just how much thinking this model is doing in that black box. Over a specific tracking period, they logged 1.74 billion prompt tokens sent to the model.
Okay.
That resulted in 36.6 million completion tokens, the actual answers given to the users. But tucked inside that process, hidden in this new array, were 30.3 million reasoning tokens.
So that means the model is spending almost as much time thinking out loud internally as it is generating the final output. What's fascinating here is the architectural requirement this imposes on developers. The documentation is incredibly explicit. This isn't just a neat debugging feature that you can look at and throw away. It is a structural necessity for maintaining state in a continuous application.
Why is that? If I just want the answer, why do I care about keeping it scratchpad?
Because of how transformer models handle context. If you are building a multi-step agent workflow, say an agent tasked with researching a company, analyzing their financials, and writing a report.
That agent is going to make dozens of sequential API calls.
Right. It reads a document, thinks about it, decides what to search next. When you make that next API call, you cannot simply pass back the user's initial prompt and the model's previous final answer.
You need the scratchpad.
If you drop those reasoning tokens from your prompt history, the model loses the logical breadcrumbs it used to arrive at its current state.
It's like having a coworker who shows you 3 pages of complex scratchpad math before giving you the final quarterly budget number.
Yeah.
If you ask them to revise the budget a week later, and you only give them the final number without their old scratchpad, they have to redo all the math from scratch to remember how they got there.
That is a perfect analogy. The model needs to see its own prior thought process to pick up exactly where it left off. If you don't pass back the reasoning details array, you induce a form of artificial amnesia.
Wow.
It forces developers to be much more meticulous about memory management. You are no longer just storing a simple chat history of user prompts and assistant replies in your database. You are structurally required to store and index the assistant's internal monologue.
And this internal reasoning is clearly paying off in the raw performance metrics. I want to touch on 2 specific benchmarks mentioned in the sources. The Crypto Briefing article highlighted the GDP-Val benchmark.
Right.
For you listening, GDP-Val is a benchmark specifically designed to measure professional knowledge work. It's not just simple code completion. It tests the ability to synthesize disparate documents, plan strategically, and output complex formatted professional reports.
It's a tough test.
The article notes that GPT-5.2 was sitting at about 71% on that benchmark. GPT-5.4 has jumped to 83%. It is matching or exceeding industry professionals in 83% of complex comparisons.
That leap from 71% to 83% is monumental. GDP-Val is notoriously resistant to simple pattern matching or memorization. It requires true cognitive synthesis. Reaching 83% suggests that the model is no longer functioning as a probabilistic text generator. It is operating as a reliable cognitive collaborator.
And over on the Reddit forums, users are celebrating similar gains in the ARC-AGI2 benchmark. ARC, the abstraction and reasoning corpus, is infamous because it's essentially an IQ test for AI.
Yeah, it's brutal.
It presents visual grid puzzles that require the model to infer underlying logical rules from a few examples and apply them to a new grid. It's something humans do intuitively, but AIs historically fail at completely because it requires abstract reasoning, not just text prediction.
Exactly. The fact that users are noting significant improvements in ARC-AGI2 confirms that the unification of the Codex logic engine with the GPT reasoning engine has resulted in a massive upgrade in raw cognitive horsepower. However, and this is the most critical, however, of this entire analysis, this raw power is deeply intrinsically tied to how the model handles its working memory. Which brings us to the most contentious, heavily debated aspect of this entire release.
Yes, this is where things get spicy. Let's pivot slightly and dive into section 2 of our outline. I've been calling this the 1 million token trap in my notes.
A very fitting name.
Because if you look at the OpenAI marketing, the 1 million context window is the absolute star of the show. It's plastered everywhere. But if you look at the developer reality, it is a technical minefield.
Truly.
We pulled some incredible insights from the r/Codex subreddit, and there's a highly respected top 1% contributor there, named Spy Mouse in the House, who's practically shouting from the digital rooftops, warning developers not to get distracted by the 1M context.
It is a vital warning. This highlights a classic disconnect between isolated laboratory capabilities and messy production reality.
Spy Mouse in the House is emphatic about it. They say, and I quote, "Guys, don't be excited about 1M context size. It's clear from their needle-in-the-haystack eval, it drops exponentially after 256K.
Let's break that down for the listener.
Yeah, what exactly is a needle-in-the-haystack evaluation, and why is an exponential drop after 256,000 tokens such a big deal if the model officially supports a million?
The needle-in-the-haystack, or NIAH evaluation, is a standard industry test to measure context retrieval degradation. You take a massive block of text, say 1 million tokens of random essays and articles. That's your haystack.
Okay.
Then you insert one highly specific random fact deep inside that text. For example, the secret password to the server is blue kangaroo. That is your needle. You then prompt the model to read the entire million tokens and ask it what is the secret password.
It sounds simple enough. It just has to use its search function right.
But LLMs don't have a traditional search function like a database query. They use attention mechanisms to weigh the relevance of every token against every other token.
Right.
What the community is discovering, and what Spy Mouse in the House is pointing out, is that while GPT-5.4 will technically accept a 1 million token prompt without crashing, its ability to reliably parse, weigh, and reason over that data degrades severely the further you push it.
So the attention mechanism gets overwhelmed.
Yes. There is an exponential drop in accuracy after the 256,000 token mark.
It's like asking a human to read a 1,000-page legal document in one sitting, and then asking them a highly specific question about a subclause on page 742.
Exactly.
They might have read the words, but the working memory is exhausted.
And the failure modes are insidious. Another developer in the threads, Toronto YYZ, noted that past 50% of the window, so around 500,000 tokens, the model doesn't just fail to find information. Subtle hallucinations begin to creep in.
Oh.
The model starts confidently inventing details, or worse, misinterpreting the logical relationships between different parts of the context. It might take a variable defined on page 10 and accidentally apply it to a function on page 800. For complex reasoning tasks, a 1 million token window is currently an illusion of capability.
And here is the kicker. It is not just a technical illusion. It is a massive financial hazard.
Yeah.
This is where we get into the hidden costs and configurations of the API. A lot of users on the subreddit, like Spike-Spiegel92, were highly confused on launch day.
They were booting up their command line clients, ready to dump massive repositories into the model, and they were still only seeing the old 258K token limit.
They thought the release was bugged.
But it wasn't a bug. It was a highly intentional safeguard by OpenAI's engineering team.
Right. The 1 million context isn't even turned on by default. It is tucked away behind a manual override.
Yep.
A user named just_Lingonberry_352 had to explain to the forum that to use the full 1M context in the command line interface, you actually have to dive into the system files and manually edit the config.toml file.
You have to explicitly write the lines model_context_window equals 1 million and model_auto_compact_token_limit equals 900,000.
By default, OpenAI ships the CLI operating at a much safer, much more reliable 206K limit with an aggressive auto-compaction algorithm running in the background to keep the context clean.
The fact that it is disabled by default, requiring a manual override in a configuration file, is the loudest signal OpenAI could possibly send to developers.
Precisely.
It essentially says, yes, we built this massive engine so we can put it on a billboard, but as engineers to engineers, we strongly advise you to keep the governor on. They know the reliability drops, and more importantly, they know the compute costs skyrocket non-linearly.
Oh, the compute costs. This is the financial invariant that developers are currently discovering the hard way. Multiple users in the deep dive, including unusual_test71A1 and rollertoaster7, have highlighted a brutal hidden economic reality in the API pricing.
They found that pushing the context window past 272,000 tokens triggers an automatic 2x usage cost multiplier.
Let that sink in for a moment.
Yeah.
If you send a prompt with 250,000 tokens, you pay the standard base rate.
Right.
If you send a prompt with 275,000 tokens, the cost of that entire prompt is doubled.
It is honestly hilarious in a dark developer pain sort of way. The model literally taxes you for making it read too much.
It's like walking up to a consultant, dropping an entire encyclopedia on their desk, and asking them a question. They're saying, sure, I'll read this, but I'm charging you double overtime for the migraine you just gave me.
That's exactly it.
This completely changes the calculus of how you build an application. In the old days, well, last year, the lazy way to build an AI coding assistant was just to dump your entire code base into the prompt every single time the user asked a question.
You can't do that anymore. Not unless you want to bankrupt your API budget in a single afternoon. You have to be surgical. You have to use RAG, retrieval augmented generation, to only pull the specific files needed.
But to be perfectly fair to OpenAI, if we zoom out and look at the competitive landscape, the 1M Context Club is a very tough place to be right now for any foundation model.
They are pushing the absolute boundaries of physics and silicon.
Right. Let's look at the competitors mentioned in the threads. We already talked about Anthropic's Opus 4.6. Spy Mouse in the House claims that despite its incredible reasoning capabilities, Opus 4.6 starts to struggle heavily at just 32,000 tokens.
And then you have Google's Gemini Pro.
Yeah, a user named Bandash of Dash Horses pointed out that while Gemini technically boasts a 1 million token context, and has for a while, it constantly suffers from severe amnesia.
It forgets earlier instructions and loses track of longer architectural plans in real-world use.
The industry as a whole is hitting a massive friction point between raw memory capacity and the attention mechanics required to actually use that memory.
So this raises an important question for you, the listener, as you design your systems. Is the 1M context just a useless marketing gimmick? Should you just ignore it entirely?
The answer from the community is no, but you have to use it correctly. There's a highly specific correct use case for it, and it is definitely not complex logic or multi-step reasoning.
It is what developers are calling data dumping.
A user named Smoke for Sanity provided two brilliant concrete examples of when to actually engage that manual config.tompole override and use the massive window. In the first instance, they needed to reverse engineer some heavily minified code.
For those unfamiliar, minified code is source code that has had all spaces, line breaks, and human-readable variable names stripped out to reduce file size for web delivery.
It is completely unreadable to a human.
It looks like a solid wall of random text.
Exactly. So Smoke for Sanity didn't try to parse it file by file. They just dumped 700,000 tokens of raw minified JavaScript into GPT-5.4 in a single prompt and asked it to map out the core functions.
And the model exceeded expectations. It nailed it.
In another case, the same user dumped 500,000 tokens of raw Discord chat history, months of back-and-forth arguments, memes, and technical discussions, and asked it to do a one-shot Q&A to summarize a specific technical decision made in the past.
And again, it worked perfectly. That is the crucial distinction you have to internalize. Massive context windows in this generation of models are optimized for single-pass retrieval and summarization.
They're built for finding the needle or summarizing the haystack.
They are not optimized for maintaining a complex, evolving state of logic over a long dialogue. If you need to search a massive server log file for a specific anomaly pattern, the 1M window is the best tool on the planet.
But if you are trying to architect a multi-tier cloud application through an interactive back-and-forth dialogue spanning 50 prompts, you need to stay far under that 256K threshold.
You need to rely on the CLI's auto-compaction features to constantly prune the context tree, keeping the model's attention focused, sharp, and cheap.
Okay, let's move out of the context trap and pivot to section 3 of our deep dive. Because if stuffing the context window isn't the best way to get this model to do complex work, how is it supposed to execute massive tasks?
That leads us to the engineering upgrades.
And honestly, this is the stuff that feels like we are living in a sci-fi novel. Let's talk about dynamic tool search and native computer use. Because GPT 5.4 isn't just a brain sitting in a text box anymore. It has hands and eyes.
The Crypto Briefing article laid it out very clearly. This release introduces native OS-level integration.
GPT 5.4 can natively interact with operating systems, websites, and desktop applications via simulated mouse clicks, keyboard inputs, and visual processing.
We need to pause and appreciate what this means. This is a fundamental paradigm shift in human-computer interaction. We are moving from conversational agents to digital operators.
Previously, if you wanted an AI to interact with a web browser to, say, book a flight, you had to write incredibly complex, brittle scripts.
You usually relied on DOM parsing, where the AI reads the underlying HTML code of the website, and then a separate layer of code you wrote had to translate the AI's text output into an API call or a web scraper action.
If the airline changed their HTML layout by one line, your entire AI agent broke.
It was exhausting to maintain. Native computer use collapses that entire stack. The model isn't reading the HTML code. It is processing the visual state of the screen exactly like a human does.
It looks at the pixels, identifies the submit button visually, and directly outputs the X and Y coordinates to move the operating system's mouse pointer to that button and execute a click.
It is wild.
In the Reddit thread, developers are already pushing it to the limit. A user named Fate of Muffins casually mentions using this feature alongside Playwright Interactive for automated browser playtesting.
Instead of writing rigid test scripts for their web app, they just tell the AI, try to break my checkout process.
And the AI visually navigates the site, clicking buttons, filling out forms, trying to find edge cases. And another user, just Randy, notes that native computer use is looking incredibly promising for noticeable everyday workflow improvements.
Agents are no longer just text in, text out. They are actively driving the user interface. Imagine the implications for accessibility or for automating legacy enterprise software that doesn't even have an API.
You just point the AI at the screen and give it a goal.
Right.
Imagine asking your assistant to audit the quarterly expenses. It doesn't query a database. It literally opens Excel on your desktop, clicks the file menu, scrolls through your spreadsheets, visually reads the columns, types out an email to your accountant, and hits send.
The boundary between the AI and the operating system is completely dissolving.
But wait, if we're talking about system efficiency, while the visual aspect of computer use is the most visceral change, the back-end upgrade to how tools are handled is arguably more important for developers.
This brings us to the new dynamic tool search feature. To appreciate how elegant this is, you have to understand the massive constraint developers faced last week.
Okay, break down the old constraint for me. How did we use tools before GPT 5.4?
In older models, if you wanted your AI agent to have access to external tools, let's say you wanted it to have a calculator, a weather API, a database querying function, and a GitHub commit tool.
You had to load the complete JSON schema and definition for every single one of those tools into the system prompt.
Every time you sent a message to the model, you're sending thousands of tokens, just reminding the model, here's the dictionary of tools you possess, here are the parameters they take, here is how you format the request.
It was a massive tax on your context window and your API budget. It was essentially context bloat. You were filling up the model's working memory with the instruction manual for tools it might not even use in that specific conversation.
Exactly.
If I just ask the AI what is the capital of France, you shouldn't need to read the manual for the GitHub commit tool before answering.
But GPT 5.4 changes that entirely with dynamic tool search. It dynamically locates and uses external tools on the fly without needing all those definitions loaded into its active memory up front.
But wait, I have to push back on this.
Okay.
If it's dynamically fetching tool definitions on the fly, doesn't that introduce massive latency issues?
If it has to stop, search for a tool, read the manual, and then execute, isn't that much slower than just having it all preloaded in memory?
Yeah.
That is the brilliant part of the architecture. OpenAI has essentially decoupled the tool definitions from the active conversational context window, but they are cached at the API layer. The model now acts more like a modern operating system.
Okay.
Think about how Windows or macOS works. When you boot up your computer, it doesn't load every single piece of software on your hard drive into your active RAM. It dynamically loads a DLL, a dynamic link library, only when a specific function is called by the user.
Okay, that makes sense.
This dynamic fetching allows developers to build massive agentic systems with access to thousands of potential enterprise tools without suffering any context penalty or massive latency spikes until a specific tool is actually required by the workflow.
It makes multi-step tool-heavy workflows exponentially more efficient and, more importantly, financially viable because you aren't paying to send a giant tool dictionary with every single prompt.
Which perfectly transitions actually leads us into Section 4 of our outline, the developer vibe check and known failure modes.
Because while the architecture sounds elegant on paper, the reality of deploying frontier models in the trenches is always messy.
Always.
The r/Codex community has been stress testing this thing nonstop since it dropped, and a consensus is starting to form around the optimal workflow stack. It's fascinating how quickly developers adapt.
A username that just_Lingonberry_352 outlined what they called an unstoppable setup.
And the interesting thing is they aren't using the fancy new GUI. They are living entirely inside the terminal, inside the Codex command line interface.
Terminal workflows are always where the real power users gravitate because it allows for maximum scripting and automation. But what is their specific stack?
They use a multi-model approach, which is interesting given that we just talked about unification. They use the ChatGPT Pro 5.4 interface, the conversational one, to draft a highly detailed PRD,
For our non-engineering listeners, a PRD is a product requirements document. It outlines exactly what a piece of software should do, its constraints, its edge cases, and its architecture.
They spend a lot of time chatting with the pro model to get this document perfect. Then they take that meticulously planned document, drop it into the CLI, and hand it over to the specific GPT-5.4 high API model to actually execute the implementation and write the code.
That workflow highlights a deep maturity in how systems engineers are utilizing these models. They recognize that despite the unification, you still want to isolate your planning context from your execution context.
They are no longer expecting one massive prompt to do everything.
They are using the conversational capabilities of the Pro interface to establish the strategic architecture, and then leveraging the high-throughput specialized execution of the high model for the actual heavy lifting.
It is a simulated managerial structure. The pro model is the lead architect. The high model is the senior developer.
Furthermore, another user, Josh Tivard, pointed out a recent UI/UX update that reflects this industry-wide need for iteration speed. OpenAI just rolled out a new fast mode toggle, distinct from the standard mode, to the GUI client on macOS.
Right, because when you are iterating on code, waiting 40 seconds for a highly detailed, deeply reasoned response is maddening.
Developers are optimizing for iteration speed over raw context depth. Give me a fast, mostly correct answer that I can test, rather than a slow, perfectly reasoned essay.
But it's not all sunshine and perfect code generation. This raises the most important question for anyone listening who is building products right now. Where is this model failing?
What is the actual threat model for engineers trying to put GPT 5.4 into production today?
This is my favorite part of the deep dive. The early adopters have identified several incredibly specific and somewhat bizarre failure surfaces. Let's look at failure mode 1, overcorrection on websites.
A user named PrestigiouSpite reported a deeply frustrating issue.
They noted that the model struggles massively with exact specifications for legal passages or compliance text. If you give the model a specific piece of legal text, say terms of service clause, and tell it format this into HTML for my website, do not change a single word.
It frequently alters the content anyway. It tries to improve or paraphrase text that absolutely must remain verbatim.
This is a classic alignment tension, and it is a massive headache in enterprise deployments. These models undergo months of RLHF, reinforcement learning from human feedback.
They are heavily, heavily fine-tuned to be helpful.
They are rewarded for fixing grammar, improving sentence flow, and making text more readable. But when you're dealing with strict legal, medical, or compliance text, that innate helpfulness becomes a severe liability.
The model basically thinks it's a helpful editor, but it's actually committing malpractice.
Precisely. The core invariant, the strict rule that the text must not change under any circumstances, is being overridden by the model's deeply ingrained alignment to edit and improve.
System designers listening to this need to understand that you cannot rely on the model's own restraint in these scenarios. You must implement strict pre- and post-processing validation checks in your architecture.
If you have a block of legal text, you should use classical hashing or diffing algorithms outside of the LLM to compare the output against the input, ensuring that designated text blocks pass through the model untouched.
That makes a lot of sense. Trust, but cryptographically verify.
Moving on to failure mode 2, which is just a hyper-specific character encoding quirk that drove one developer absolutely insane. The same user, PrestigiouSpite, noted that GPT 5.4 has a known persistent issue rewriting German rollouts.
For example, it will take the letter A, the A with the 2 dots over it, and it will actively expand it into the characters A.
Now, technically, AE is an acceptable alternative spelling in German when an umlaut key isn't available on a keyboard. But if you're generating front-end code for a premium German client, you want the actual laut.
It's a tiny detail, but it's the kind of thing that makes a code base look unprofessional and drives quality assurance teams crazy.
I actually have to laugh at this one because character encoding has been the bane of software engineers since the dawn of the internet. It is deeply ironic that a trillion-parameter frontier AI is making the exact same localization mistakes as a 1990s web browser.
But technically, it speaks to the tokenization process.
How does the tokenizer cause this?
Language models don't see letters. They see tokens, which are chunks of characters mapped to numerical IDs. The tokenizers are heavily biased towards standard ASCII characters because the vast majority of their training data is in English.
When the model processes non-standard UTF-8 characters like an umlaut, its internal representation might map it to a sequence that is statistically closer to an E in its latent space.
It is optimizing for a normalized, safe output rather than a faithful transcription. Again, this requires developers to build specific sanitization and localization layers to catch these linguistic artifacts before they hit production.
It's fascinating that we're building the most advanced technology in human history, and we still have to write regex scripts to fix evals. But the most fascinating bug to me by far is failure mode 3, phantom errors.
Prestigious Fight, again, perfectly captured this phenomenon. The model will literally hallucinate error messages.
When it is using its native computer use capabilities or generating UI code, it will frequently generate and display red error banners or warning content on the screen as if a critical error has occurred, even when the system state is perfectly fine.
As the user eloquently put it, when does it make sense to display something? When should it be omitted? GPT models really struggle with this.
This failure mode cuts to the absolute core of how large language models process information and why they are fundamentally different from classical software. They are at their root predictive text engines.
They are predicting the most statistically probable next sequence of tokens based on the context.
So why does it predict an error when everything is fine?
Think about its training data. In millions of GitHub repositories and Stack Overflow posts, complex code execution is almost always followed by developers discussing error logs.
If the context of the conversation closely resembles a complex scenario where an error usually occurs in the training data, the model might predict that generating an error message is the most statistically probable next action.
It doesn't actually know the ground truth state of the application. It is just mimicking the pattern of complex action followed by error message.
It's like a hypochondriac doctor who reads so many medical textbooks that they assume every patient with a cough has a rare disease. It's failing to maintain the invariant of only display an error if a true exception has actually been caught by the system.
Exactly. And this is why autonomous agents utilizing computer use need rigid, deterministic state machines wrapping their logic. You cannot let the LLM directly update the UI state based on its own predictive generation.
The LLM should propose an action, but a deterministic classical supervisor program needs to verify the actual state of the application before that action or error message is rendered to the user.
Which brings us to a somewhat sobering realization from the developer community and a look at the future of engineering. Despite all these massive paradigm-shifting upgrades, the 1M context, the native computer use, the dynamic tools, the unified reasoning engine.
A user named Bobby Rickies pointed out a rather stark mathematically grounded statistic. They noted that across all these updates, there was only a 0.9% improvement on a specific, rigorous software engineering benchmark compared to highly optimized prior workflows.
Just 0.9%.
And their conclusion in the thread was profound. I guess we hit the wall with LLMs.
That is a chilling thought for the industry, but one that systems engineers have been anticipating. The community is beginning to recognize the asymptotic limits of single model scaling.
What does that mean, the asymptotic limit?
It means that the curve of improvement is flattening out. You can only pump so much raw data and compute power into a single transformer architecture before the returns diminish entirely.
Going from a 10 billion parameter model to a 100 billion parameter model yields massive gains.
Going from 1 trillion to 10 trillion parameters might only yield a bare 0.9% improvement in actual verifiable logic. The consensus, as articulated by Bobby Rickies, is that the next massive paradigm shift won't come from OpenAI releasing a GPT-6 that is 10 times larger.
So if making the brain bigger doesn't work, how do we get better AI?
It will come from architectural complexity outside the model. It will come from managing swarms of specialized smaller agents working in concert, checking each other's work, and crucially, it will come from formalizing verifiability.
And the Rice/Codex community actually used a specific term for this formalization of verifiability, ralphing. They said the goal for the next year of AI engineering is for ralphing to become the default state.
It's an interesting piece of community jargon. What does it entail functionally?
From what I gather, ralphing is this idea that you don't just rely on the AI to generate code and hope it works. You have an entire surrounding framework dedicated to mathematically or logically verifying that the code does exactly what it's supposed to do without unintended side effects.
You force the AI to write the tests before it writes the code, and then an external system runs the tests.
If the tests fail, the loop restarts without human intervention. It's about building trust through rigorous automated evaluation, rather than blind faith in the model's predictive output.
Ralphing, or whatever the academic term eventually becomes, represents the true maturation of AI engineering. We are finally moving away from the era of prompt engineering as some kind of mystical art form where you just ask the AI nicely and hope for the best.
We are entering the era of systems engineering. The LLM is no longer the entire product. It is just one highly capable but ultimately unreliable component within a highly structured, self-correcting, verifiable workflow.
It is the fundamental acknowledgement that AI will always make mistakes, and the value lies in building architectures that anticipate, catch, and correct those mistakes autonomously.
And that brings us to the end of our outline for today. Let's synthesize all of this.
Yeah.
What is the so what for you, the listener? Whether you are a solo developer hacking on a weekend project or a systems architect at a Fortune 500 company, what do you need to take away from the release of GPT 5.4?
First, it is undeniably a monumental leap forward in capability. The unification of the Codex and GPT lines into a single entity streamlines development and eliminates the routing dilemma.
Second, the visibility into its reasoning process via the reasoning details array gives us an unprecedented structural ability to manage state in complex applications.
And third, the native computer use and dynamic tool search are opening doors to entirely new classes of software that can navigate the OS just like we do.
But, and this is the crucial operational takeaway, you must respect the physical constraints of the system. That 1 million token context window is a hazardous, highly expensive zone. It is a siren song for lazy architecture.
Unless you are doing a massive one-shot data dump for retrieval, like parsing 700,000 tokens of minified code or searching massive log files, you need to stay far away from those upper limits.
It's just not worth the 2x financial penalty and the hallucination risk.
Exactly. If you are designing systems today, my professional advice is to build your core architectures around the reliable default 256,000 token window. Utilize the CLI's auto-compaction features to aggressively manage your state.
Leverage the dynamic tool search to save on token costs and reduce latency. And most importantly, if you are experimenting with these new UI driving agents, the ones utilizing native computer use to click around a screen, you must implement strict deterministic evaluation harnesses.
You need classical state machines to verify everything. Do not let the model drive the car without a heavily reinforced seatbelt and a secondary hard-coded braking system.
Trust, but cryptographically verify. Absolutely. And that leaves us with a final provocative thought, something for you to mull over as you digest all this technical density. We've spent a lot of time today talking about GPT 5.4 being capable of dynamic tool search.
Meaning it can proactively find, fetch, and use external tools that you didn't even explicitly load into its memory.
And we've talked extensively about its ability to natively control a mouse, type on a keyboard, and visually navigate a live operating system.
The boundary of what this AI can access is no longer a static list defined by the developer. It is entirely fluid and agent-driven.
Exactly. So here's the question for all the systems engineers listening. If an automated agent can independently alter its own tool set on the fly and navigate a live, unpredictable OS environment, how do you design a fail-safe evaluation harness?
How do you reliably test a system that is constantly changing its own parameters and discovering new ways to execute its goals?
It is the ultimate paradox for the next generation of quality assurance. How do you build a deterministic test for a non-deterministic actor that is capable of rewriting its own operational rules?
I highly encourage you to explore that question on your own. Think about the system constraints, the invariants, the failure modes we've discussed today.
If you come up with a novel test, a new architectural approach, or even a refutation of the current limitations we've outlined, we want to hear it. Build it out, test it, and always encourage listeners to give their take in the comments below. We read them all, and it's how we all get better at building these systems. Thank you so much for joining us on this incredibly deep dive into GPT 5.4. We'll see you next time.